Hello. Happy Friday, everybody. I'm happy it's Friday. It's been a really long week. Need a weekend. Yeah, it's true you still have school, but that's okay. I have a warm up for you to do while we wait like 10 more minutes. Actually, that's way long. Maybe 5, maybe 2. Hi, JC. Hi, Madison and Heavenly. Oh, hey, Heavenly. I haven't heard from you yet. Hello, everybody. Happy Friday. While we're waiting, try the warm up. Hi, Lisa. Hi, Anna. Hi, Stephanie. Hi, Jalen. Good morning. Hi, Jasmine. Hi, Eleanor. Hi, Becca. Hi, Aiden. Yeah, I'll get you after. I can't take attendance right now, so I do it after, but I got you. Good morning, patients. Hi, Emily. Hi, Harley. Hi, Brendan. And Miguel. Okay. That's 5 minutes. We're gonna do the warm up really quickly because it's applicable today. So first of all, thoughts. Today's lesson is gonna be probably a little bit different than what we're used to with Trig, and I just want to say this before we start, that the meat of the Trig unit is the first 2 lessons that we did. So expect most of your tests to be on the first 2 lessons we did. Of course, the other stuff will be on there, but if you start feeling worried, especially about these last couple of lessons, um, just know that most of the test is going to be from the first 2 lessons. So, speaking of the first 2 lessons, on our warm-up today, sine is the opposite over the hypotenuse. And from From the reference angle of theta, which is the yellow one on my screen, opposite is 3 and hypotenuse is 5. Cosine is the adjacent over the hypotenuse. And from the reference from the pink angle, which is alpha, that weird fish symbol is alpha. No, thank you, Patience. I'll make sure that you get marked present for the other day. So the adjacent side on this triangle, the adjacent one to the pink angle, is 3. So we're ending up with the same fraction for both of these, 3/5. And the next question is, why do you think these values are the same? Essentially, and we'll talk about this in a little bit in the lesson, but when you have a triangle like this, the adjacent to one of the reference angles is the same thing as the opposite to the other reference angle. So when you take sine of this angle and cosine of this angle, they end up being the same value, just because that opposite and adjacent switch that happens. And we're going to use that today in one of our identities. So we're on page, what page is this? 42 today in your green book. So have that out if you don't already. Hi, Shelby. Okay, so the 8-4, we're talking about trig identities, and we call them identities because they are, essentially we're talking about things that are equal, which sounds kind of funny, but identities just mean things that are equivalent. And we can use trig identities to rewrite trig statements and simplify them, which becomes very helpful when you're trying to solve things that are look complicated. So we're going to learn those trig identities today. They'll become more useful to you in secondary 3, but we're going to use them today to rewrite different statements. So the first identity that we're going to learn is the complementary identity. If you recall, complementary are two complementary angles add to be 90 degrees. And we have a triangle here with a 90-degree angle in the corner here. Oh no, my highlighter's too big. 90-degree angle in the corner there. Let me zoom in. And then we have the angles A and B in the rest of the triangle. So we all know that 180 degrees is what all the interior angles add to, but notice that 90 of those 180 degrees are already used up in the 90-degree angle. And so A and B by themselves also add to be 90, so that we have a grand total of 180 inside this triangle. So we have two angles, A and B, that add to be 90 degrees. And that means that they are complementary. So A and B, we call them complementary angles. Is that right? Nope. I skipped a syllable. Complementary. That's better. Good. So we have A and B that are complementary, and just like we sort of discovered in our warm-up today, when you take sine of one of those angles and cosine of the other angle in the triangle, they end up being the same values. Robbie, calm down. You can't take notes and be annoying at the same time. Take notes. Okay, so we have two complementary angles, and when we take sine of one of them, it equals cosine of the other one, which is what this says. We have two angles. I don't actually want to highlight them. So we have two angles. Let's highlight the triangle angles and the ones in here. So the blue angle is one of our complementary angles, and 90 minus that angle will give you the the other angle, right? The pink angle. So we essentially just have these two things that are equal. We have sine of one angle is equal to cosine of the other angle in the triangle. Cosine of 90 minus the angle we started with for sine. So in our triangle, we're saying sine of A is equal to cosine of B. But if we don't want to reference two different angles, we can just say one is theta and the other one's 90 minus theta. Guess what, Robbie? You can pause the video if you want me to slow down. It's great. But please ask questions if you have them. I bet it stopped working. Okay. I'm just looking at my notes here. I think that I did this backwards. Although this is true, I am going to switch this to be B and A so that my colors will match because I know you guys and I know that you care about that. There you go. So essentially you can take sine of one angle in a triangle and cosine of the other angle and they will be equal. That's our first identity. The second identity we're learning is the quotient identity. Quotient, this word is just a really fancy word for fraction, quotient, two things divided by each other. So it turns out that tangent of an angle is equal to sine of that angle divided by cosine of that angle. And that is, we actually learned that last time when we were learning the unit circle. Tangent was the one that is dividing the two sine value and the cosine value. So this is just a reminder of that. Just as a thought, these angles do need to be the same for this to be true. You can't just take sine of a random angle over cosine of a random angle. They all have to be the same. But tangent is the quotient, is equal to the quotient of sine over cosine. Tangent is sine over cosine. So we're gonna pause and do some of these problems on the bottom before we learn our last identity. And stay with me here. These are not like solve. That's not what we're trying to do on these problems. We're trying to get this piece. Let me use my fancy laser pointer, I guess. We're trying to get cosine over sine to equal 1 over tangent, and we're trying to illustrate that by having steps in between to sort of show how one will equal the other eventually. Hi, Tom. So here's my tip for these. It's best when you're looking at a fraction like this to sort of separate them out. I don't know. I might take that back. For this first one, I'm gonna say that later. So just hang on to that thought for a second. So right here we have cosine over sine, and we're trying to prove, that's what these are, they're proofs. We're trying to prove that it equals 1 over tangent by replacing things with their identities, just like the identities that we just learned. And here's my first step for this one. Just, yeah, stay with me here. So cosine over sine, we know that tangent is sine over cosine. It's the other direction. So what I'm going to do is I'm going to write this as 1 divided by sine of theta over cosine of theta. And let me explain myself here. Remember that when you divide by a fraction, it's the same thing as multiplying by its reciprocal. So what I'm rewriting cosine over sine as 1 divided by sine over cosine because that is equal. Because if we were to divide by that fraction, we would have to flip it over, and that's what we started with. So cosine over sine is the same thing as 1 divided by sine over cosine. And sine over cosine is the identity for tangent. We can replace sine over cosine with tangent, and that's going to be my next step. Let me put an arrow so we're being consistent here. 1 over tangent, 1 divided by tangent, which we can rewrite as 1 divided by tangent of theta, which is what we wanted it to equal. Do you see that? So we're just trying to bridge that gap between this and show that they are equal, in fact, using identities, using just things that we can manipulate in that expression, just like I replaced cosine over sine with 1 divided by sine over cosine. And as soon as we've bridged that gap like this, then we're done. That is what the problem is asking about. So number 2, we have sine of theta plus cosine of 90 minus theta. So this is going to be using, you might notice already, that's going to be using the first identity that we talked about, this one, with sine of theta equals cosine of 90 minus theta. So this piece of our equation right here, I just want to replace cosine of 90 minus theta. I know because of my identity that is the same thing as sine of my angle, sine of theta. I just replaced cosine of 90 minus theta with sine of theta. I didn't change this first sine of theta. That's gonna just stay the same. And now we have this. We have sine of theta plus sine of theta, which are two of the same things. It's kind of like having x plus x, which we can rewrite as 2 times sine of theta, 2 times that value. And that's the gap we were trying to bridge. Notice that now it's equal to 2 times sine of theta. Robbie, literally you can't type that much and take notes at the same time. Okay. Are there any questions so far? I'm gonna start this next one because there's like a lag, but if you have questions, please ask. Okay, for number 3, feel free also to pause me and try these on your own because normally in class I would let you try them on your own, but feel free to pause me and then see if you got it right. For this one, I am going to replace tangent, and just so you know, there's not only one way to bridge this gap, there's actually a lot of different ways, and so if you end up bridging the gap a different way, that's perfectly fine as well. There's no like one right way to do this, is what I'm trying to say. So I'm going to replace tangent of theta with its identity up here, this sine over cosine. I'm just going to replace that because I'm trying to make it equal sine of theta. That's my goal down here. And so I'm going to replace tangent of theta with sine of theta over cosine of theta. Just like that, I just replaced tangent with its equivalent, with its identity. And then you might notice that we have divided by cosine and multiplied by cosine, which I guess if it's easier to see, you can rewrite this as like sine of theta times cosine of theta over cosine of theta. That's what would happen if you multiplied those two things. and those cancel, which is brilliant because we wanted it to equal sine of theta, which then bridges that gap. Okay, we're going to learn one more identity, and then we're going to try some more of those proofs, identity proofs. The last identity that we're learning is the Pythagorean identities, and they're called that because they come from the Pythagorean theorem. So recall this image from forever ago. We were using triangles. We have to remember our unit circle. So we put like right triangles inside the unit circle. And that was to figure out what those sine and cosine and tangent were actually doing, which was finding side lengths of triangles inside of the unit circle. So if we look at that triangle, which has one side length of cosine of theta, one side length of sine of theta, and the hypotenuse is 1 because it's inside the unit circle. Pythagorean theorem tells us that if we square both of the legs and add them together, it equals the square of the hypotenuse. A squared plus b squared equals c squared. We're pretty familiar with the Pythagorean theorem, hopefully. And then what you can do with that equation is just replace A, B, and C with what we have in this triangle over here. So like we'll replace A with cosine, B with sine of theta, and C with 1. So in those blanks go these expressions. Cosine of theta, sine of theta. I'm just replacing A, B, and C with the values from that unit circle triangle. This is just explaining where the Pythagorean identity comes from, because it's good to understand that stuff. So now we've replaced it. We have an expression that says cosine of theta squared plus sine of theta squared equals 1 squared. And 1 squared is just 1. It doesn't get any bigger. And so we end up with cosine of theta squared plus sine of theta squared. I'm going to write them closer to the squared because I don't want them to be separated. Equals 1. And that's the Pythagorean identity. If we square cosine of an angle, yes, c does equal 1. If we square cosine of an angle and square sine of an angle and add them together, it's always going to equal 1, which is pretty cool. Just so you know, there's this weird convention, and I'm not sure who started it or why, in math, but having cosine of theta squared, you can also write it cosine squared of theta. Those things are equal. That's just like a weird notation thing. We just move the squared in front of the cosine. I don't know why. That's true, Nick. If you square rooted that whole side, it would also equal 1. You're right. That identity doesn't become super helpful because we don't usually see the square root of cosine theta squared plus sine squared theta squared. But you're right, that is the same. Hi, Sarah. So yeah, that's just a weird notation thing you might see. Actually, I'm pretty sure you will see sometime in your life. I think that they did that just because it looks good, which I mean, I agree, it kind of looks nice, but it also becomes confusing. Like I remember thinking, okay, I know sine theta squared, I know that, but what is sine squared of theta? Same thing. They just write them two different ways. Again, don't really know why. I think it's just an aesthetic thing, but I don't know. Let's highlight again because I like that. Okay, there you go. So we have Pythagorean identities. Yes, but only for a square with a hypotenuse of 1, Nick. Otherwise, that does not work, right? Because usually c squared is not the same thing as c, but in this particular instance, it is, because remember that the trigonometric functions are they're tailored specifically to those triangles with a hypotenuse of 1, and then we scale them depending on what triangle we're dealing with. So the answer is yes, but only in this triangle. Only in triangles with hypotenuse of 1. And no, Becca, sine and tangent, all trig ratios, trig functions, sorry, I can't talk. It's the end of the week. All trig functions you can write with the squared in between the theta and the cosine. That's just like a weird thing they do for all trig functions. I'm not sure why. Okay, so we're going to keep going. We're going to try some other proofs here. Not all of them use the Pythagorean identity, but some of them will. Okay, so the first one, I would recommend that you pause this video, actually, if you want to, and do number 1 and 2, because they're using mostly just algebra. There is one trig identity that you use in number 2. So pause me now, try those on your own, and see if you can bridge that gap. Okay. For this first one, hopefully you're used to enough multiplying fractions together that you can tell that this, oops, that's a highlighter, that this is going to be equal to cosine of theta over cosine of theta. Cosine of theta times 1 over cosine of theta is just the same thing as dividing by cosine theta, which you might notice cancels and becomes 1, which bridges that gap. We wanted it to equal 1. So that one wasn't bad, hopefully. Sine, so now, okay, so we're trying to make sine theta times 1 over cosine theta equal tangent theta, which, again, we're using the same multiplying fractions logic to say that this is equal to sine theta over cosine of theta, which is our identity for tangent. So we are just going to replace that with tangent of theta, which is what we wanted. Okay, number 3, we have tangent over sine of theta. Here's where, remember when I started saying something at the beginning of this and retracted it. So it's a lot of times it's easier to see what things are transforming into if you sort of separate out fractions. So right now we have tangent of theta over sine of theta, but I'm going to rewrite it as tangent of theta times 1 over sine of theta. I'm kind of doing the reverse of what I did in the previous problem, because I want it to equal 1 over cosine, and so I know something is going to cancel, but I hate having a fraction over a fraction divided by another fraction. So I'm trying to separate out my fractions so that I can turn tangent into its own fraction and see what's happening. So speaking of which, I'm going to take tangent and replace it with sine of theta over cosine of theta, because that's the identity. And it still equals 1 over sine of theta. And you might notice that since we're multiplying these fractions, we have sine of theta over, well, it's times 1, but we don't really care about that. Cosine of theta times sine of theta on the bottom. Because when you're multiplying fractions, you just multiply across the top and across the bottom. And then we have the sine thetas that cancel, which gives us 1 over cosine of theta, which is what we were trying to get this whole time. Okay, remember that if you have questions, please ask. Okay, we have a couple more on this last page. So that's a good question, Becca. Um, what we're not doing is we're not like solving the problem. We're not like we already know that it simplifies into this and we're trying to bridge that gap. We're trying to say why, which is what a proof is. And I know that we have had very little exposure to what like proofs mean, but proofs like are essentially trying to get from one point A to point B in like a in a way that you can explain each step. And so these are not necessarily, we're not, I like, if we know, even though we know what it ends up as, we're trying to prove it by showing what each step and like sort of why each step works. Because seeing that like tangent times cosine, which is what we're on right now, tangent times cosine is equal to sine, you might not necessarily immediately be like, oh, I know exactly why that happens. So we're just trying to bridge that gap. On your homework, just so you know, there's some problems that just say like simplify, and so there is no like end goal, and your job is to figure out what the end goal is. These ones I feel like are a little bit easier because you know what you're shooting for. Um, because it turns out that there's a lot of different ways that you can manipulate trigonometric identities, and so having an end goal in sight is actually helpful. So as long as you can follow the steps, you'll be okay on your homework. But we're just saying why. We're answering the question why. Why is this the same as this? Like, what makes that true? Robbie, I swear. I don't know how you're disruptive when you can't even. Anyway, okay. Let's try this one. Tangent. I'm gonna replace tangent with sine over cosine. Oops. And we still have times cosine of theta, which ends up canceling because we have divided by cosine of theta and multiplied by cosine of theta, so it ends up being just sine of theta. You're right, Robbie. Probably not even taking notes, which is what you should be doing. Okay. Now we have sine over tangent times 1 over cosine. So these are getting a little bit more complicated, so I want to make sure that you're understanding what my logic is here. Again, I'm going to separate out the fractions. Whenever there's a tangent in a fraction, I just want it its own because I know that I'm probably going to have to replace it with sine over cosine, and I don't want to do that inside of a fraction. So I'm gonna say this is like sine of theta over 1 times tangent, times 1 over tangent of theta times 1 over cosine of theta. So all I did was I separated out this fraction into sine of theta over 1 and 1 over a tangent of theta. And this is the one that I want to focus on, 1 over tangent of theta. We actually proved something at the very beginning of our book, and I'm just going to split back there really quickly. Notice that we have 1 over tangent is the same thing as cosine over sine. Like, because tangent of theta is sine over cosine, the inverse, like 1 over tangent, is going to be the upside down version of the other fraction as well. So 1 over tangent is cosine over sine. So I'm going to replace my 1 over tangent with like the upside down version of the identity for tangent, which is cosine of theta over sine. It's the upside down version of tangent because this is also upside down. Okay, so I've replaced 1 over tangent with this cosine theta over sine of theta, and we still have a couple of other, scroll for crying out loud, there we go. We still have the other fractions that we were trying to get rid of. So I'm just going to multiply across the top all the way and across the bottom all the way. And it gives you sine theta times cosine of theta times 1, which we don't really need to write. And then sine of theta times cosine of theta on the bottom times 1, which we don't really need to write. But notice that everything cancels in that fraction, and it leaves us with just the value of 1, which is what we wanted to prove. So we have sort of bridged that gap between what it's equal to, proven it. We're answering the question why. Okay, last one. This one is going to use some Pythagorean identities here. And you know that because they're squared in here. So notice we have cosine squared of theta and sine squared of theta involved here. Hi, Philip. I'm glad you made it. You can rewind me. It's good. It's YouTube. Okay, 1 minus cosine squared of theta equals sine squared of theta. That's what we're trying to prove. So what I'm going to do, and bear with me here, is I'm going to replace 1 because I have an identity. Hang on. I have this identity that says cosine squared of theta plus sine squared of theta equals 1. So I'm going to replace 1 with all of that. I'm going to replace 1 with cosine squared of theta and sine squared of theta. That's what this is what that's going to look like. I have cosines, I guess we'll use that convention there. It's cosine squared of theta plus sine squared of theta. All of that is just equal to 1. So I'm just going to replace 1 with cosine squared of theta plus sine squared of theta. And then this minus cosine squared of theta stays. And hopefully you've noticed that now we have a positive cosine squared of theta minus cosine squared of theta, which equals 0. Yes, because we have a positive and negative, it's like having plus 1 minus 1, plus 2 minus 2. If they're the same, we can say that they're equal to 0, which leaves us with just sine squared of theta. Perhaps I'll write another step in between there just to explain why everything disappeared. I'm just going to reorder it so that we can see pretty easily that cosine squared of theta minus cosine squared of theta equals 0. And then we're just left with sine squared of theta, which is what we wanted to, one more step. There you go. That's what we wanted. Okay, I will leave that zoomed in for a second while I talk. So you do have a homework assignment using these identities. The beginning of the homework assignment is like this stuff with identities. It's simplifying and like I think there might be one proof on there. And then the end is just some applications of trig. So it's like the meat of this unit from the beginning, but used in real life scenarios. So yeah, ratio of sides stuff. I don't know if that's what you're talking about, but yes. Like, yeah. So then you'll use just normal like trig stuff from lesson 1 and 2 on the last couple of problems on your homework. Be looking out for the study groups today. I have a feeling that a lot of you would benefit from those, and um, those some of you who have not seen in those yet. They're really fun. We just sit around and like I wait for you to ask questions and you entertain me. I promise it's not scary. Um, you can have your mic and your video turned off even if you want to. So be looking out for that. I will message you guys about when those are starting. I will probably start one at like maybe 11 or 11:30 today. So be looking out for that. I will also start one probably later if you have other things to do right now. But I want to be able to help you on this homework if you need it. So please do that. Also, this is a good time for questions. I know that like I just did all those problems for you, so you probably have questions when you do the homework. So again, please come to the study groups. They're fun. You guys entertain me because I'm all by myself in my house. Oh, Nick, you must be already doing the homework, Nick. But the ratio of sides just literally wants a fraction. So like opposite over hypotenuse. Yeah. So like just a fraction. Fraction of sides. It also might, I think the first couple of problems are asking about, it doesn't have numbers. So you're just gonna have to like say the sides, like side AB over side BC or whatever. Cosine squared. You're gonna have to rewind, Philip. It just is cosine of an angle, but squared. It's just a weird notation to put the squared in between, but it's just the same thing as squaring something. I do need to get over my Minecraft phobia, but it's hard. So tangent of theta is equal to sine theta over cosine theta. Okay. Yes, Nick, but that's probably not what it's asking for. The ratio of sides is just the side lengths one over the other. Yeah. I know Animal Crossing came out today, right? Everybody's dying over that. I should play that. Yeah, like that, Nick. Okay. Again, join the study group in like 15 minutes if you have questions so that we can work on your homework together and I can help you and you won't feel lost. Because I know this stuff is new, especially proofs and like simplifying stuff. Yeah, I know. They were talking, somebody was asking me to play Minecraft, but then they're trying to get a bunch of teachers on the Minecraft server. And so I told them that I have a phobia of Minecraft. Like the blockiness is like a nightmare scape to me. So like kind of freaks me out and I don't play it. I do. Yeah, that's true. Okay, anyway, now that we've gone completely off topic, I am gonna end the stream. Yeah, I'm gonna end the stream now. But please, again, get help on your homework with, I mean, if you let me talk. If you don't want to join the study groups or whatever, just message me and I can help you as well. But study groups are good because then I can answer one question and several people hear it. It's good. Okay. All right. Bye, everybody. Have a good rest of your Friday. Hopefully, I will see most of you at some point today in a study group. Bye.